Hello students, and welcome again. I'm going to start our discussions on chapter 3, which is about computational statistics, things that we'll now start to measure or look at when we want to calculate numbers to go along with the graphs that we have already been looking at and discussing today. So the topics we'll cover here are summaries for the center of the distribution and the spread for both symmetric and skewed distributions. We'll look at summaries for variation. Of course, we've already got the variation included up above in the spread, but we'll look at both variability and the center of the distribution. Then we'll cover something called the empirical rule and z-scores. These will be used very much throughout all of our training. And the last thing we will cover are the box plots and what's called the 5-number summary. It's a very simple way of summarizing numerical data, but very useful, particularly when your data can be divided into groups. And we'll talk about those at the end of this chapter. So that's the topics that we will be covering. Let's move on here and get started. So for symmetric distributions, you know we talked a little bit about this already, about shape, outliers, center, and spread. And we learned ways to describe the center and the spread of a distribution. And we talked about the shape and outliers. That was primarily chapter 2. So now we're going to talk about these measures. Statistical measures that are very commonly used. And when I use the word statistic here, it does have the meaning that something that is calculated from our data, something that is both numerical, but it's also a characteristic of the sample from which we are collecting our data. So for symmetric distributions, the mean, which is the center of the distribution, it's something we're all very familiar with, and you probably learned at a very young age in arithmetic class how to calculate the mean. So it is intended to be a good representative statistic that represents the typical value of the data set. So here's a distribution of college entrance ACT scores for a sample of statistics students, and you see that the center of that distribution is somewhere a little less than 25, and it's shown there on that graph, dot plot in this particular case of the data. And when the data is symmetric, then the mean is a good representation, whereas you have skewed data, and so we have this distribution here that's skewed to the right with the long tail on the high side. And these are salaries of professional baseball players from 2010. The mean is it's an interesting statistic here. It may not be all that typical. In other words, if you want to know what your typical baseball player is making, the mean may not be that representative, right? As it says on this slide, you think the mean is a good representation. And the answer is no. However, if you are the team owner and you're paying out these salaries, that mean is a meaningful number, if you will, because it's the average of what you're paying. So I don't want to downplay it completely, but I will say that we have other numbers that are probably best quoted with the mean, particularly the median, that is more true representative of what's going on. But to just throw out the mean and say no, it doesn't have any meaning, that's not correct either, particularly when the data is in dollars, as this one is, because all of those dollars are very real and they are being paid to these baseball players. And on average, you know, if you have 25 players and they're each and their total salary is $125 million, then the average would be $5 million that you're paying each player. You see that the majority of players don't make that kind of money here. But the ones that do really skew the average, and that's going to happen. So we'll look at other statistics, particularly the median here. So In a symmetric set of data, though, the mean does represent a typical value. For skewed distributions, it's not a good estimate of typical value, although it's certainly not without meaning. But what happens is the mean gets pulled towards that long tail, because when you average the data in, certainly those large numbers are going to have an impact. When I was looking into statistics as a major, they told me what the average salary was of their graduates from the previous year, and it was rather high. It was more than engineers were making, and I was kind of surprised at that. And after they had their fun with you, they would tell me that, well, they had 12 graduates, and 11 of them were working as statisticians, and the 12th was a professional athlete, a quarterback for the Chicago Bears, which is an NFL football team. And so he was making a lot more money than the rest of those statisticians, and as such, the mean was much higher than you would have expected. So maybe still a valid statistic, but you have to be careful about how representative it is. We're going to look at the hurricane data again here. This is a slightly, at least the summary that is shown here is slightly different than the one that we saw in Chapter 1. You might remember that the mean deaths were lower than this. Well, we had thrown out some outliers, some really unusual observations. But the point here is you could see for this large set of data, and this describes the data a little bit more thoroughly. It says that we had two large hurricanes, Katrina with 1,833 deaths, and Maria with 3,057 deaths. And when those outliers were put in with the rest of the data, you had a mean number of deaths from the hurricanes of 177. And for the male named hurricanes, the average was 17.7. There were two outliers in that data set, and you can see that in the graph. The graph is not totally representative of the data, because on the female named hurricanes, you can see that the largest number is 150. It doesn't go out to 3,057. So let me just say that the graph is a little bit inconsistent with the numbers that you see, and someone created those numbers with the full data set, and then they produced the graph that didn't have the full set of data on the female side. And at some point I need to correct that, just so you understand what's happened there. But those numbers are so far out, the 3,057, it would really skew the graph a little bit. So someone made the choice to remove them at some point. And so that's why I redid the numbers in Chapter 1, but I decided to leave them here because it's trying to make the point that those extreme numbers have a big impact. Now, is that death number, 177, representative? Not really, but there were that many people that died. You take 177 and multiplied it by the number of hurricanes that we have, that would give you the total number of deaths. So in some ways it's a meaningful number, but it's maybe not as typical as what you would like to see when you use a summary statistic like the mean or the median. The mean is a very easy number to calculate. I think we all know how to do it. You add up the data values in the data set, all of them, and you divide by the sample size, n. So if I had 100 hurricanes, I would add up all the deaths and divide that by the 100 at the end, and that's how you get the average. The formula for that in Greek notation says the summation of all the values, summation of all the y values, we usually or the x values, divided by n, is equal to the mean. And you can do that in a small data set, but in a large data set it becomes very difficult to do the calculation by hand and not make any mistakes. So we use technology to do that. In particular, in this class, we will use StatCrunch. If you've seen the StatCrunch video for Chapter 2, there is a short addendum to that. The shorter video on StatCrunch shows you how to calculate the summary statistics in StatCrunch. And for the TI-84, the command is there to take the to get the statistics for one variable in X bar. Then X with a bar over it is the mean, and we will use that terminology here in this class as well. X with a bar over it means the average of all the values. So I hope you can see this. Sometimes my little picture might get in the way and I might move it around a little bit, but we have a sample of the cost of 1 gallon of gas at 10 different gas stations in a neighborhood in Austin, Texas on a fall day in 2013. That's enough information. And you see the values. So there's some variability there. Not all the gas stations are charging the same price. And we want to know, what is the typical amount? If you randomly picked a gas station, what typically would you expect to pay? And for the, I've got a typo on this slide that's supposed to say the dot plot. Estimate the typical value. I'll fix that in the one that I publish. But estimate the typical value, and so you pick a value right in the middle there somewhere. It looks to me like it's somewhere just above $3 would be what would be typical of this. So you took a look at that. You estimated the typical value, and what does it mean? It means that that's about what we would expect to pay if we randomly picked a gas station. Now, some of you are bargain hunters, and you'll probably pay less than that because you'll look for the gas station that has the lowest price. But you could think of this as what would be typical to pay if I picked any gas station at random, right? And so on this particular day, the average was indeed, if you take that data and average it, you get $3.02 as the price, typical price for a gallon of gasoline. So how close were you? Usually you get pretty close from just looking at the data and estimating it. That's the sign that a graph has been very useful here. And so I guessed about $3.04, so that's a little high compared to the value of 302, but it's pretty close. And you would expect to be fairly close from just looking at the data. But obviously we would want to calculate the mean. Now, is the mean an appropriate measure for the center of this data? That's a loaded question. There might be an outlier there at $3, close to $3.20. So the mean might be a little skewed because of that. The median is $2.99, which may be a little better measure, but to me, if I'm paying that much for gas, $2.99 or $3.02, not that much different. So don't get too excited about this at this point. This isn't a highly skewed distribution. It's just one where we only have 10 data points. But we'll talk more about this idea of the median versus the mean. The reason that the mean is higher is because that high number, 320, is probably pulling the mean in that direction, and it doesn't have the same impact on the median, right? So this distribution isn't totally symmetric, but they're not far apart. We'll see distributions where they are far apart, but here they are not that far apart. All right, if we had this data in StatCrunch, we could do this manually if somebody didn't give us the file, and say the gas prices go from they've been sorted here from high to low, except for the last, well, no they haven't. They're not sorted. I apologize for saying that. We have the 10 observations. They're listed there. There's the graph that's been constructed. That's a dot plot. And you know how to do that now, I think. If you go to summary stats, and it's shown right here at the top. Maybe I could move this to the bottom. Summary stats columns, and you pick the column that has the data, gas price in this case. It will then turn around and give you the result, which is that average of $3.02, rounded to 2 decimals is $3.02. It also gives us some other numbers, which we'll talk about shortly, but the median there is the middle value, that half the data is above $2.99 and half is below $2.99. All right, and on the TiO2, you would do it. Here are the commands to do that same thing in the TI-84. Excuse me, it's the TI-84. Once you have entered the data, I'm going to stop right there. We'll come back to this.